Hi, this video presents the architecture of a 2D graphics system, identifies the roles of important libraries like the OpenGL or GLOT, introduces a simple view of the GPU, and provides the first OpenGL programs. From system point of view, a graphics application handles the user input, changes the virtual world by modeling or animating it, and then immediately renders the updated model presenting the image to the user. This way, the user immerses into the virtual world, and he feels that he is promptly informed about its current state. The process from the input to the virtual world is called the input pipeline. Similarly, the process mapping the virtual world to the screen is the output pipeline. The complete system is a loop with two important points, the virtual world and the user. In the output pipeline, the virtual world is vectorized first, since only points, lines, and polygons can be transformed with homogeneous linear transformations. Then, modeling, view, and projection transformations are executed, moving the current object to normalized device space. Here, clipping is done, then the object is transformed to the screen where it is rasterized. Before being written into the frame buffer, pixels undergo pixel operations, needed for example to handle transparent colors. The frame buffer is read periodically to refresh the computer screen. The user can see the screen and interact with it by moving the cursor with input devices and starting actions like pressing a button. Such actions generate events, taking also into account the screen space position. The unit here is the pixel. Note that screen space is different for the operating system and for OpenGL. For the operating system, axis Y points downward, while in OpenGL, axis Y points upward. Thus, this Y coordinate should be flipped. That is, we have to subtract the Y coordinate from the vertical resolution. The input pixel coordinate goes from the screen to modeling space in the input pipeline. Thus, the inverse transformations are applied in reverse order. With input devices, not only the virtual world can be modified, but also the camera can be controlled. Our graphics application runs under the control of an operating system together with other applications. The operating system handles shared resources like the input devices and the frame buffer as well, so a pixel data in the frame buffer can be changed only via the operating system. Modifying pixels one by one from the application would be too slow, so a new hardware element, the GPU, is introduced. The GPU is also a shared device and can be accessed via the operating system only. Such accesses are calls to a library for the application program. We shall control the GPU through a C graphics library called OpenGL. On the other hand, to catch input events handled by the operating system, we need another library. We use the FreeGLOT for this purpose, due to its simplicity and portability, because it runs on various operating systems. The operating system separates the hardware from the application. The operating system is responsible for application window management and also letting the application give comments to the GPU via OpenGL, not to mention the reprogramming of the GPU with shader programs. OpenGL is a collection of C functions of names starting with GL, and the second part of the function name shows what the function can do, and the final part allows to initiate the same action with different parameter numbers and types. To get an access to the GPU via OpenGL, the application should negotiate this with the operating system, for which operating system dependent libraries are needed. Using them is difficult, and more importantly, it makes our application not portable. So to hide operating system dependencies, we use GLOT, which translates generic commands to the operating system on which it runs. It is simple, and our application will be portable. GLOT functions are start with GLOT. The graphics output is implemented by OpenGL. The application window management and the input are responsibilities of GLOT. Our application consists of a main function and a set of event handlers. In main, our application program interacts with GLOT and specifies the properties of the application window and also sets event handlers. An event handler is a C function that should be programmed by us. This function is connected to a specific event of GLOT, and having established this connection, we expect GLOT to call our function when the specific event occurs. A partial list of possible events are the display event that occurs when the application window becomes invalid, and thus GLOT asks the application to redraw the window to restore its content. The keyboard event occurs when the user presses a key having an ASCII code. Special event is like the keyboard event but is triggered by a special key having no ASCII code. For example, the arrows or the function keys. Reshape event happens when the dimensions of the application window are changed by the user. Mouse event means that the user pressed or released the button of the mouse. Idle event finally indicate some time elapsed and our virtual world model should be updated to reflect the new time. Event handler registration is optional with the exception of the display event. If we do not register a handler function, nothing special happens when this event occurs. Primitives like line or triangle mesh go down the pipeline, each having multiple vertices associated with their homogeneous coordinates and possible attributes, for example, the vertex color. Primitives must be transformed to normalized device space for clipping, which requires the transformation of its vertices with the modeling, viewing, and projection transformation matrices. Clipping is done so is homogeneous division if the fourth homogeneous coordinate is not 1. Then primitive is transformed to screen space, taking into account the viewport position and size. The primitive is then rasterized in screen space. So that's the basic output pipeline that is implemented by the GPU. So for performance reasons, OpenGL 3 or 4 retained mode requires the application to prepare the complete data of vertices and attributes of a single object rather than passing them one by one. These data are to be stored in arrays of the GPU, and these arrays are called VBOs or vertex buffer objects. An object can have multiple VBOs. For example, we can put coordinates in a single array and vertex colors in another. Different VBOs are encapsulated into a vertex array object, or VAO for short, that also stores information about the data should be fetched from the VBO and sent to the input registers of the vertex shader. Single input register of the vertex shader can store 4 32-bit long words. This 4-float structure is called VEC4 in GLSL. The input registers are called vertex attrib array. The responsibility of the vertex shader is to transform the object to normalized device space. If the concatenation of model, view, and projection matrices is given to the vertex shader, it is just a single matrix vector multiplication. The output of the vertex shader goes to output registers, storing the vertex attributes and also the location of the transform point. This location is called GL position. and the fixed function pipeline assumes that this register gets the location of the point in normalized device space. Clipping, homogeneous division, viewport transformation, and rasterization are performed by the fixed function hardware of the GPU, so these steps cannot be programmed. The output of the rasterization step is a sequence of pixels with pixel coordinates and interpolated vertex attributes. Pixel coordinates select the pixel that is modified in the frame buffer. From other vertex attributes and global, so-called uniform variables, the pixel color should be computed by the pixel, or also called fragment shader. Let us zoom out the connection of the vertex buffer objects, vertex shader input registers called attrib arrays, and vertex shader input variables. The object described in arrays are called VBOs. For example, coordinates can be stored in one array, colors in another. To allow the vertex shader to process a vertex, its input registers must be filled with the data of that particular vertex, one vertex at a time. A function called GLVertexAttribPointer tells the GPU how to interpret the data in VBOs from where the data of a single vertex can be fetched, and in which attrib array a data element should be copied. For example, coordinates can be copied to attrib array 0, while colors to attrib array 1. When the vertex shader runs, it can fetch its input registers. It would not be too elegant if we had to refer to the name of the input register, for example, like attrib array 0, so it is possible to assign a variable name to it. For example, attrib array 0 can be vertex position, or attrib array 1 can be vertex color. Note that this was only one possibility of data organization. For example, it is perfectly reasonable to put all data in a single array where coordinates and attributes of a single vertex are not separated. In this case, the GLVertexAttribPointer should tell the OpenGL where an attribute starts in the array and what the step size, so-called stride, is. So we are ready to implement our first OpenGL program. In the main function of a graphics application, we set up the application window with the help of GLOT, telling the initial position, size, and what data should be stored in a pixel, and also what functions should be called when different events happen. At the end, the message loop is started, which checks whether any event occurred for which we have registered an event handler. And if this is the case, it calls the respective event handler. The main function can also initialize data in OpenGL, especially those which are needed from the very beginning of the program execution and which do not change during the application. We need shader programs from the beginning, so this is a typical place to compile and link shader programs and upload them to the GPU. So let us start with the main function. Two header files are needed. Windows.h is needed only if the program runs in a Microsoft Windows environment. So glue is the OpenGL extension wrangler library that finds out what extensions are supported by the current GPU in runtime. It is our interface to OpenGL, which works even if we select a higher OpenGL version that is supported by the header file in our computer. For example, if we have an MS Windows system, it is very likely that our OpenGL header and library files support only OpenGL 1.0, while we want to work in OpenGL 3.3 or even higher versions. The difference is made by glue. GLOT is a windowing utility toolkit to set up the application window and to manage events. In the main function, first the application window is set up with GLOT calls. So GLOT init initializes GLOT and allows to use to communicate with the GPU via OpenGL. GLOT init context version sets the required OpenGL version number. In this case, we want to have OpenGL 3.3. GLOT init window size specifies the initial resolution of the application window. GLOT init window position specifies where it is initially placed relative to the upper left corner of the screen. GLOT init display mode tells GLOT what to store in a single pixel. In this case, we store 8-bit RGB and also alpha values in 2 copies in order to support double buffering. GLOT create window creates the window which shows up. High graphics will be the caption bar text of that window. Then glue is initialized. We set first this glue experimental to true, which means that glue obtains information on the supported extensions from the graphics driver, so even if it's not updated, then it might not report all features the GPU can deliver. Setting glue experimental to true gets glue to try the extension even if it is not listed explicitly by the driver. This is indeed magic. Glue init makes the initialization. From here, we have an initialized OpenGL. Please do not call any OpenGL functions before this point. GL viewport sets the render target, which is just a photograph inside the application window. On initialization is our custom initialization function that will be discussed on the next slide. The remaining functions register event handlers and start the message loop. For the time being, only the onDisplay is relevant, which is called whenever the application window becomes invalid. We use this function to render the virtual world, which consists of a single green triangle directly given in normalized device space. So first we set up the application window with the resolutions 600 × 600. Then with GL viewport specify the viewport that covers the whole application window. And this viewport corresponds to a square of corner points -1, -1 and +1, +1 in normalized device space. So if we give a triangle with 3 vertices, coordinates of the vertices are between -1 and 1, we will have a triangle that is inside the viewports on screen. In initialization, those OpenGL data are initialized that are typically constant during the application, so they do not have to be set in every drawing phase. In our program, this includes the shader program and a single object, which is going to be a simple triangle. Objects are identified by vertex array object identifiers. So the shader program and the VAO are global variables because they are set in the initialization, but they will also be needed during the display function. First, we allocate one vertex array object and its ID will be called VAO. With binding, this is made active, which means that all subsequent operations belong to this VAO until another VAO is bound or the current one is unbound with binding 0. In the second step, one vertex buffer object is allocated, which will be part of the active VAO. This vertex buffer object is made active again with binding, so all subsequent operations are related to this until another one is bound. Array called vertices stores the geometry of our triangle and it is in the CPU memory. It contains 6 floats, that is 24 bytes. With GL buffer data, the 24 bytes are copied to the GPU. With the last parameter of GL buffer data, we can specify which type of GPU memory should be used. We say here that 24 bytes will be copied, and we also specify the starting address for the copying operation. Note that so far we said nothing about the organization and the meaning of the data. It is simply 24 bytes. The GPU doesn't know that it defines 3 vertices and each with 2 Cartesian coordinates which are in float format. This information is given by the GL vertex attrib pointer function. So GL vertex attrib pointer defines the interpretation of the data, and also that the data associated with the single vertex goes to the input register number 0. So it specifies that a single vertex have 2 floats, that is 8 bytes. If it was a non-floating point value, it would also be possible to put the binary point to the most significant bit, but here we use floats, so there is no normalization, therefore this parameter is set to false. The last 2 parameters tells the GPU how many bytes should be stepped from one vertex to the other. If it's 0, data in the array is tightly packed. Stride and offset parameters in the last row are essential if interleaved VBOs are used. The remaining part of the on-initialization gets the shader programs ready. The source of the shader program can be read from a file or directly copied from a string. We use here the latter option. As programs are typically written in more than one line, the string cannot be a simple C-like string, but should be special and hold new line characters as well, which is possible with this raw string definition of the C++ programming language. The vertex shader source code starts with the version number, telling the compiler how matured the GPU is assumed during execution. Uniform parameters are like constants that cannot change during the drawing of a single primitive, and all vertices share these uniform parameters. MVP, uniform variable, is a 4x4 matrix. Its type is Mat4, which represents the model view projection matrix. The vertex shader has one per vertex attribute defined with variable name VP and storing the XY coordinates of the current vertex. The vertex shader code computes the multiplication of a 4-element vector, that is the conversion of VP to normalized device space. The result is written into the GL position output register, which should contain the transpond point in normalized device space. The vertex shader would output other variables as well, which would follow the point during clipping and rasterization and would be interpolated during these operations. Clipping, homogeneous division, viewport transformation, and rasterization are fixed function elements that cannot be programmed. The output of the fixed function part is a sequence of pixels, also called fragments, belonging to the current primitive, and also the variables that are output by the vertex shader, having interpolated for the current pixel. The pixel address is in register GL frag code, which cannot be modified, but from the other registers and uniform variables, the color of this fragment can be obtained by the fragment shader processor. In the case of our fragment shader program, it has only one uniform input called the color, which will determine the output color stored in output variables outColor. The implementation of the fragment shader is very simple. The uniform variable is copied to the output color, extending with a constant 1 alpha value. The very beginning of the pipeline, vertex coordinate variable VP is connected to the vertex shader input register, also called attrib array number 0, as told by the location equals to 0 statement. The output of the process is the out color variable that is connected to the frame buffer with the GL bind frag data location function. So let us summarize what we have here. We have two strings defining the source codes of the vertex shader and the fragment shader. Then first we ask for an identification number of the vertex shader program, upload our source code to the OpenGL library and compile this source code. We do the same with the fragment shader program. First we ask for an identification number, upload the source code and compile the source code. Then shader program is created and we attach the compiled vertex shader and fragment shader to the new shader program, specify final output of the pipeline that will go to the frame buffer. Well, it is the out color output variable, link the program and finally activate this program. So from this point, this vertex shader and fragment shader will run. We have registered a single event handler called onDisplay that reacts to the event occurring when the application window gets invalid. In this function, the virtual world, which consists of just a single green triangle, is rendered. First, with GL clear color, we set the color with which the application window will be cleared by the so-called GL clear function. Here, GL color buffer bit stands for the frame buffer, storing color values only. Drawing consists of setting the values of uniform variables of shaders and then forcing the geometry to go through the pipeline, which is called the draw call. This is the draw call. Finally, the buffer used for drawing so far is swapped with the buffer the user could see so far by the GLOT swap buffers function. So the result of the rendering will be visible to the user. The fragment shader has a single uniform variable called color of type vec3, which can be set with the function glUniform 3f. Here 3f tells us that this function has many different versions and we are using that version which has 3 float input variables. The glUniform function needs the location or the address of the uniform variable. This location can be obtained with the glGetUniform location function, giving the name of the uniform variable. The vertex shader has just one uniform variable, the model view projection transformation. We basically do the same. First we ask for the location and then modify the MVP with the prepared data and using the location information. Here in the glUniform matrix 4 function FV means that we use that version of glUniform matrix 4 that uses float numbers, and instead of listing all 16 parameters of a 4x4 matrix, we just give the starting address of the target matrix. Two-dimensional array can list elements in two different orders. It can be row major when first rows are specified, or column major where columns follow each other. In the glUniform matrix 4 function, glTrue tells OpenGL that the given data should be interpreted as a row major matrix. Before calling the draw call, we have to bind the array, which vertex array object that should go through the rendering pipeline. The glDrawArrays has 3 variables. The first one specifies what kind of object should be fit to the list of vertices encoded in VBOs. Here we say that we need triangles. The VBOs should be fetched from the very beginning, from index 0, and 3 elements should be fetched from the VBO. OpenGL supports various primitives. Here is the summary of OpenGL primitives. But these are basically just points, line segments, and triangles, but there are sophisticated options where we can share vertices if it's possible. Points are points. GL lines require a pair of vertices defining the start and end of individual line segments. GL line strip assumes that the endpoint of a line segment is the start of the next, so shared points should be specified only once. GL line loop is similar to GL line strip but adds one more edge between the last and very first vertices. GL triangles require vertices of multiples of 3, and each 3 vertices define a new triangle. We use it, for example, when the polygon is decomposed to triangles with the ear clipping algorithm. GL triangle strip needs 3 vertices for the first triangle, then any additional vertex introduces a new triangle of the last, previous, and the previous of the previous vertices. GL triangle fan can be used for convex polygons. Here again the first 3 vertices introduce the first triangle, and then any new vertex adds a new triangle of the last vertex, previous vertex, and the very first vertex.